Hello everyone, welcome to the EasyPower Tuesday Refresher Series. My name is Jim Chastain, an Applications Engineer here at EasyPower. And we appreciate your attendance today and your support of EasyPower. This is a second installment of a four-part series on the introduction to protective device coordination. And today we'll be focusing on fuses. And as we are in the habit of doing, I'd like to start with the poll question, and we appreciate your participation and feedback. So the first question is, which type of protective devices do you most often use? And this is just a broad assessment of what you think your preference is or the type of devices you use most frequently. And I think part of the interest, the heightened interest in this topic, is the inclusion in the National Electrical Code specific requirements, new specific requirements regarding energy reduction, and we will spend a fair amount of time talking about that. So it looks like we have a quorum on this. Here's how folks have weighed in, and I'm a little bit surprised that fuses is not that more highly sought after, which is fine. Then the second question is, when using fuses, what area of the application causes you the most difficulty? And again, maybe it doesn't apply to the whole audience, but this is the topic that we'll be talking about today. Again, this is not going to be an exhaustive investigation of fuses, but primarily looking into how EasyPower represents the technical parameters and how that can be used in your decision process. So it looks like we have a quorum here, and the distribution looks close to what I suspected. So thank you very much for participating. As I kind of mentioned, our agenda is basically to touch on these topics: series rating, series coordination, and then the guidance that the National Electrical Code gives us regarding fuses, specifically discussing current limiting aspects of it, and then the arc energy reduction area. Now, as we covered in the more detail in the first installment last week, protection is pretty much a necessary factor in the design to prevent equipment damage, reduce the risk of fire or explosion, increase the safety for personnel in the area, potentially meet legal requirements, and insurer requirements. The process of coordination is the area of protecting the equipment and hopefully isolating a fault as close to the faulting device, the offending area of the system, so we don't de-energize unnecessarily greater portions of our facility based upon a single fault. Now, when we get to talking about selective coordination, this is specifically requires that we slow down devices upstream to allow the downstream protective devices to sense the fault and do their job. And because of that, there can be a conflict of interest, if you will, regarding the coordination aspects of the project. And so it's something of a balancing act. The twin goals of maximizing protection and maximizing coordination very often directly conflict, and the protection engineer must strike a reasonable balance between the two. And some of that can be company policy, some of it can be recommendations as far as personnel safety. So that's where things get into a little bit of a sticky wicket. Now, in terms of fuses, they offer some clear advantages regarding breakers. Generally, they're a lower cost solution. They do have the ability to be current limiting, although some breakers now include current limiting capabilities. That means that they have the ability to trip during the first half cycle of a fault if they're in the current limiting range of their performance curve. They also offer the highest interrupt rating of protective devices. And that downside or a con of using fuses is the fact that they're a one-time device, so you must have spares to replace or re-energize once you've had a fault. They are very useful in arc flash reduction, but in the case of a fault or a single fuse blowing, there's a potential risk of single phasing the equipment, which could be cause more injurious in terms of the equipment risk. And then there's the possibility, and we run into this a lot during a study, is the potential for replacement with the wrong fuse, and that would effectively change the results of, in particular, an arc flash study, whether it was recognized at the time or not. Now, the NEC, specifically in Article 110.9 in definitions, defines that equipment intended to interrupt current at fault levels shall have an interrupt rating at the nominal circuit voltage that's at least equal to the current that's available at the line terminals of the equipment. And this is referred to as the rating of that interrupt device. And fuses generally have an extremely high interrupt rating, and if they're selected properly, the several fuse types can be acceptable in what's regarded as a tested series combination. What this is referring to are terms that we refer to as interrupt fully rated, where all the protective devices in my design have individually the rating to sustain the arc current or the fault current for that particular bus. So for instance, in this particular example, we have a predicted short circuit available fault current of just over 31,000 amps. Each of our devices is rated for 65,000 amps interrupting, and consequently there's no problem with the protective devices being fully rated. Now in EasyPower, this is basically the default mode, and as long as we have the part modeled in the design or in the digital model and connected to the device library datasheet, that information comes from the manufacturer's datasheet. And so that's why you'll see me when I'm doing demonstrations reiterate the need to make sure we've connected that device on our model to the device library. And that function is part of the calculate button on the short circuit tab of each protective device. Now, when we have the downstream system that's not rated to that short circuit current, in this case, we have the same 31,000 amp available short circuit current on this bus, but these particular devices are only rated for 10,000 amps, then we would have an issue. And part of that, a solution, a potential solution for that would be to utilize an upstream device that has been tested and provides what's called series rating. In this case, we're using a fuse that's rated for 65,000 amps, and the manufacturer of the breakers has tested the potential survival of this type of device when subjected to the rating current of the upstream fuse. So both devices are likely to clear on the available fault current of 31,000 amps. So this potentially interferes with series coordination. But you'll find it on price competitive commercial projects where you want to use potentially a lower cost breaker on the feeders. Now, EasyPower does not provide series rating for fuses, so that improvement as far as the rating needs to be manually entered on and is based upon the manufacturer's test reports. When a breaker is used for this upstream device, then that again is going to be a tested pair, if you will, between an upstream device and a feeder device. And EasyPower does provide series rating for breakers, and with the admonition that if you change the upstream device type, you potentially may lose that aspect of series rating. So part of this discussion is a stage in doing the modeling or the analysis called equipment duty, and that's why it should be a portion or a significant step in my short circuit analysis. So John is asking, why doesn't SNC SMD 34.5 250E in the database? Okay, John, good question. And that's one you'd want to submit to tech support. But we'll take a note and talk about it offline, and I need to speed up my reading. So again, the bottom line is there's a potential for series rating to enhance the protection, but just by and this needs to be a tested result per the manufacturer. It's not something we just can put into the software without that backup. Now, we all agreed that coordination, selective coordination, is the process of trying to make sure that the first upstream protective device from the fault will trip prior to or before any protective devices further upstream. And so the process of, as I mentioned, of doing that potentially could interfere with the calculations for arc flash, because as a result, we have to use a slower device upstream. And one of the solutions or potential offering in the fuse arena is the ability to use different types of fuses. And specifically, one of the most advantageous is a current limiting fuse. Unfortunately, not all fuses are current limiting. So this again goes back to understanding what's projected on the TCC curves. Likewise, not all fault current will fall into the current limiting range, even on a current limiting fuse. So again, it's important to know what the fault current is and where that stands in terms of the TCC plot. The definition of a current limiting fuse is that the max it will clear on the fault current within the first half cycle of the fault. And when we talk about the TCC curves, by convention, the bottom of the TCC plot is 0.01 seconds. Well, the first half cycle time is 8 milliseconds, so that's actually below the plot of our curve. And so when we see fault current that's above the plot line or the TCC plot, the inference is that it's going to trip the fuse sometime before the 0.01 timeline. If that information is provided EasyPower, then we will plot the curve below the 0.01, but if it's not provided, the curve stops at that point. TCC curves, the data from manufacturers comes at us and is available in several different forms. So consequently, you'll see a thin line on some fuses or a thicker line on others. And it depends on how the manufacturer has rated the fuse. The left-hand side of the thicker curve is defined as the minimum melt, current, and time, and the right side is regarded as the max clearing time. Now, when a manufacturer provides one or the other, for instance, this may be the minimum clearing time, then there will be a percentage ratio that is predicted for the maximum clearing time. Likewise, the manufacturer may provide an average melt time, in which case EasyPower would buffer that with a plus and minus parameter to give us the minimum and maximum clearing time. Now, the significance of that is at any given current, because this is an inverse curve, there can be a relatively wide spread between the minimum clearing time, which is the lower edge of the curve, and the max clearing time, which will be the upper right-hand side of where that current intersects my fuse line. Now, as a side note, where this comes into play in arc flash calculations, there can be a time difference such that the longer time gives us a higher incident energy calculation, and that is that's required or suggested as being a more conservative approach when we're calculating arc flash incident energy. Chuck has got a question here. It may come into play. Yeah, thank you. He says it's not really on topic, so I'll kind of belay that one as well. Now, just as a side note, in current limiting fuses, and actually in most fuses, a good rule of thumb is a 2-to-1 size ratio will coordinate successive layers or successive use of series coordination using the fuses. And I think getting to Chuck's point, when we plot the transformer damage curves, again, the 100% damage curve is the dotted line, and the derated or 58% single phase to ground plot is the solid line, because the single line to ground can be a phase overcurrent. We want to make sure that our protection will protect the transformer in that case. But likewise, because the energization inrush can cause sporadic trips unnecessarily, we want to make sure that our protective device is set above that particular point, so the inrush will not cause a trip on the primary side. Now, all this is kind of more to the point of transformer protection, but this is based upon the self-cooled rating. And again, EasyPower handles the math to determine these limits. Now, in terms of coordination, the manufacturers provide to us fuse coordination tables in addition to the TCC curves. And the factor I'm trying to point out with this particular inset is that as long as we have a 2-to-1 ratio in the same family, the manufacturer is suggesting we will get series coordination. And outside of a different family, the recommendation, or in some cases it can be as significant as an 8-to-1 ratio between the upstream and the downstream plot. So what we're comparing is the same family versus a different family. We stay within the column that we select other values in an RK1 range. We could use a 2-to-1 ratio and be ensured of seeing coordination. Whereas if we jump shifted between the RK1 and the RK5 family, the manufacturer says the best we can count on is 4-to-1. Now, what this looks like on in EasyPower is something like this. So here we have series fuses, 600 amp, 300 amp, 150. So my ratio of 2-to-1 is all the same, and they're in the same family. If I plot this feeder, I can see, in fact, I do have the ability. So coordination is defined as these curves never touching each other. And so the fact that they're parallel gives me a level of confidence that I will have series coordination. Now, the fact that it intersects my motor starting curve gives me a little bit of pause. And so at that point, I need to take into account whether or not I want to use a different size fuse, or if I want to verify the acceleration time of the motor, in which case I might slow down if I had that information and looked at my acceleration time for the motor on a temporary basis, we can see that if the motor in fact accelerated slightly slower, I could ensure myself of not having the sporadic trips. Or if I pick a slightly larger fuse in the same family, I might be able to accomplish the same result. Okay, so again, the advantage of using projecting the TCC on the different loads. Again, we covered transformer curves last week and the thermal damage curves for cables. And so all we're doing here is imposing the plots for the TCC curves of the different fuses. And again, by adjusting the lowest one to be 200 amps, I may or may not be causing myself headaches. Additionally, in the National Electrical Code, there's requirements for transformer protection. And these include specific ratings or maximum protection settings for different size transformers and different conditions and different protective devices. So with a 13.8 to 480 step down on the primary side, I could utilize a 300% rating fuse sized, and on the secondary side, potentially be able to use 125% rating for the secondary protection. All right, so this again is this is all information that's covered in considerably more depth in transformer protection webinars and videos that we have on the website. So I encourage those of you with an interest to research that. In the National Electric Code, there are a number of articles that touch on or give us requirements for selective coordination. And for the most part, these are emergency or standby power supply systems for sensitive equipment and ones that we need to make sure we keep on, even in the case of faulting equipment or loss of power. And so I'm not going to go into the details on each one of these. They're well documented. What has happened or what has transpired in the 2021 version of the NEC is an information note that basically addresses the concern that some had regarding the overcurrent protection when you have a standby or emergency source. And so what this details for us is the requirement to have coordination between the D protective device and the C protective device, the C and the B and the A, without necessarily having A and B coordinated themselves. For instance, if they were the same value or the same trip time, they would not be coordinated, but they would still be qualified as far as the supply of this particular load. However, in the standby or emergency source, the requirement is to have D coordinated with C, C with F, F with E, and that basically answers the question about how do we handle the difference in fault current supplied by the emergency source versus the regular source, normal source. In 2021, there were several changes in the National Electrical Code that got a lot of attention, and part of this is due to the fact that there was not much addressing arc flash per se prior to 2021, and with the advent of Article 240.67, the National Electrical Code specifically addresses arc flash and reducing arc flash incident energy. And so it applies to fuses rated for 1200 amps or higher. The change in the code was actually included in the 2017 version, and it made this particular article effective post-dated as of January 1st, 2020, to give manufacturers the opportunity to create product that could be used in this application. And there's a lot in this particular clause. First of all, the documentation to demonstrate the method chosen to reduce clearing time and make it available to those authorized to design, install, operate, or inspect the equipment has to be provided. Second, the method to reduce the clearing time if the fuses do not clear an arc within 0.07 seconds or less shall be set to operate at less than available current, utilizing a list of specific possibilities. And then thirdly, and probably is most difficult of any of these requirements, is the need to do performance testing once we've included the reduction possibility or the reduction methodology to our particular system. I'll get into more details in a second. So the Article 240.67 only applies to fuses rated greater than 1200 amps with a clearing time longer than 0.07 seconds at the arcing current. An evaluation of the TCC curve and the arcing current is required. There's a couple of catch-22s and even in this statement. The arcing current and the calculation of arcing current is at the heart of the new and improved IEEE 1584-2018 version. And in EasyPower, it's relatively easy to calculate that arcing current, whether it's reduced or 100%. However, beyond the scope of 1584, which is beyond 106,000 amps voltage fault current, the standard does not make a recommendation. So in EasyPower, we can use the Ralph-Lee method. Well, the Ralph-Lee method doesn't utilize the arcing current; it uses voltage fault current. So we have some potential, I wouldn't say conflicts, but points of discussion even there. So let's look at specifically a series of buses that are protected by different fuses above 1200 amps and talk about it real briefly. So let me get rid of my fuse protection. So here's my 1200 amp setup. And so I go into short circuit current and fault all these buses. And then look at range for arc flash. We see that we have a selection between 1200 and 3000 amps. The arcing current has been calculated, and then the trip time, the fact that it's in magenta type, means that the reduced arcing current is being utilized for calculating instant energy. And so the trip time for each of these devices, the 1200 amp is tripping at 89 milliseconds. The 1500 amp is tripping right at 70 milliseconds, 69 milliseconds, 117, and then the 3000 amp, again, is beyond the scope of the IEEE equation, but we see a trip time of 4.49 milliseconds. So for starters, the restriction of 240.67 doesn't apply to anything with 70 milliseconds or less. So these two fuses in the range, my 1500 amp and the 2000 amp, they don't need to be improved as far as arc flash energy reduction. Whereas we have an 89 millisecond and 117 millisecond clearing time, they need to be addressed according to the electrical code. Now, the point I want to make here is when we go into the calculation methodology that's used for EasyPower, the recommendation in the standard is to use integrated method, especially if we have longer faults. Well, we're not even looking at longer faults at this point, so I want to use momentary current, which is the half cycle current. Secondly, if we're going to talk about the current exceeding the IEEE maximum, then we have to make a selection about whether we're going to use Ralph Lee or IEEE 1584 extended, which is not recommended. So let's go back and use Ralph Lee and see how that applies to our calculations. And what we get is, again, the tripping time with momentary current is still below our 70 milliseconds, but because the current is higher than my 1200 amps and we can't use arcing current, we need to come at this from another direction, and that's using the Ralph Lee equations. Okay, so at this point, we'd have to use some arc flash energy reduction methodology on these three circuits on the right. So the recommendation then for methods to reduce arc clearing time or energy is the fuse shall have a clearing time of 70 milliseconds or less at the available arcing current, or one of the following means shall be provided and shall be set to operate at less than the available arcing current. First is differential relaying, energy reducing maintenance switching with local status indicators, energy reducing active arc flash mitigation systems, current limiting electronically activated or actuated fuses, or an equivalent approved method. Now, there's a lot in that, because in the fuse arena, many of these types of devices weren't available. And so what has been proposed in differential relaying is to have a relay that has the ability to switch, once a fault is detected, to switch the fuse. So it's a fuse operated relay. And what the suggestion is it will basically redirect or reopen the current once that higher current is detected, and this can be done on a differential basis, which means it can be very sensitively set up. Likewise, with an energy reducing maintenance switch with local status indicator, this is something that can be manually operated and switch the main fuse for a current limiting fuse or a lower current alternative for the point or the time of doing the maintenance. And there really wasn't equipment back in 2017 when this was introduced that allows us to do this. So again, the delay of this requirement has now expired, and since January 1st, 2020, we have the need to have these types of equipment. So now new on the market are energy reducing relays switching devices in multiple combinations of these alternatives. And what it comes down to is a switching device that has the ability to open up that switch in line with the fuse and or put a fuse with lower trip time temporarily in the circuit. So the relay doesn't operate the fuse, it operates the switch in line with the fuse. So maybe my terminology didn't come across correctly. But the point being, the relay is operating the switch, and so the question is, how do you model this in EasyPower? Well, currently in EasyPower is the ability to do swapping of a fuse based upon a switch being in parallel with the current limiting fuse, or a lower rated fuse, such that if once we detect a fault, you open the switch and it forces the current through the more sensitive fuse. And again, this is something already in the system. What it appears from the data sheet from the manufacturer is that switch is more in series with the direct current and opens up the switching rather than redirects the fuse. At any rate, there's multiple ways to get there, and I suggest you want to talk to your hardware manufacturer, and once you've kind of decided what you want to do, make sure you request EasyPower, the model ready for you when you need to model the system. Now, one of the alternatives is an energy reducing active arc flash mitigation system that's effectively an earth grounding alternative. Once a fault is detected or an arc is detected, you ground the whole system, which forces the primary fuse to open, and much quicker than the normal fault current would require. The situation has a lot of trade-offs involved. One process doesn't necessarily fit all systems, and so I encourage you to contact the manufacturer for details to verify whether this would work for your system at all. Again, what it's going to do is clear the main fuses at a higher current, and some of the demonstrations that have been posted on the internet have been very impressive. Okay, covered a lot of ground in kind of a surface methodology, so hopefully this gave you some food for thought. What we've talked about is system coordination with fuses, kind of the trade-offs involved, that transformer protection is critical, and fuses are a key part of that, especially in fire prevention. It's very important, even more so, that proper data be entered during the modeling of the equipment so the TCC will be accurate for the loads. And in essence, whereas it wasn't the case before, arc energy reduction is now a requirement by the National Electrical Code. So it looks like we ran over our time allotment. I will, to the best of my ability, answer questions that have been submitted via email. We have regional training online set for the last months of this year, so you may want to check the website for that. And if you have other questions regarding the use of EasyPower tools, by all means contact tech support at easypower.com. Appreciate attending today, and look forward to talking to you next week. Have a good day.